a lot with the warm-up, so I think we're good. So with the shortcut, okay, the reason why it works and the reason why we can use it is that what it's doing is it's separating the difference between what's known as a core electron versus an outer electron, okay? Because if you notice, like if I were to write, so we just did silicon, okay? If I had you write the electron configuration now for phosphorus, would it be that different? Look at phosphorus in relation to silicon.
No.
Why is it not really different?
Because you just have one electron on the last one.
Yeah, the only thing that would change would just be the end one here. So it's kind of redundant to always write all of these beginning ones if we just know it's always the same. And that's where the shortcut comes in. So on your notes, you might want to label, because I gave you this configuration, but label them as these are the core electrons, and these are the outer electrons. Okay, so maybe draw some arrows and label them separately. Any ideas of why? Why do we mostly care about the outside electrons? Why would they be the most important, Mitchell?
Because the core always going to stay the same. Because you'd have to do the core electrons if there's a small number, right?
Yeah, well, and the core always stay the same, so that's a big part of it. And what else, Austin?
The outer electrons do chemical bonds.
Yeah, these are the ones that make the atom react or not react. These ones are just spinning around their whole life long, right? So really looking at those doesn't help us understand an atom any better. This is what helps us understand the atom, which is the point of a configuration in the first place, okay? So what we're gonna do is there's a very particular way in which you shortcut it. This right here is the shortcut for sulfur. So write that down on this line. So what we have is we have neon in brackets. We'll talk about that here in a second. And then we have the outer electrons, or all that come next. One other thing with the shortcut that I'm okay with, so when I learned this method myself, I don't write neon-10, I just do neon in brackets. So you're allowed to not put that -10. Even more, yeah. Because what is this -10 representing? Is that neon is 10? Yeah, so it's redundant to me to put both. Like, if you put neon, I know it's 10. So you could just do that, and then you'd have 3s2, 3p4. So any ideas of why neon was our choice for the shortcut? What do you see, Jace?
Because it's the last one on the row above the 3.
Very good. So the way the shortcut works is we're always going to find the noble gas, which is the last one, because that means it's full up to that point. So you find the nearest noble gas, that's the previous period, and then you just have to start from there. Because basically, if I have neon in brackets, you're telling me that 1 through 10 is taken care of. They're all in a room. We don't have to look at them anymore. Okay? So that's why it's always the noble gases, though. You can't just pick any element to shortcut with as well. That makes sense? Yeah, Austin?
What if you're trying to find a noble gas? It's just like neon.
Yes, so what if I told you write the configuration for neon? Sadly, you can't shortcut by just writing neon in brackets,
What you have to do.
but you could use the one above it. Yeah, so if you ever had to like write it for xenon, you can shortcut with krypton. But sorry, you can't just write it in brackets, because once again, we're trying to tell something, and that doesn't tell me much. So, okay? And then we just start on the next row and then fill the number of electrons in each sublevel. Okay, so let's try this one together. Let's do a shortcut for germanium. Okay, so look on your periodic table. Germanium's right here. Don't say it out loud, but point to what noble gas you think we'd want to use here. Point on your periodic table what noble gas you think we'd want to use. Okay, ready? On the count of 3, say it out loud. 1, 2, 3.
Argon.
Good. So this is the one, which is argon. So we're going to write argon in brackets. Now this is the trickiest part with the shortcut.
Wait, don't we have to write this, the first part? Like the, because I heard the sulfur, you had to write S16 in front of it.
Oh, for like what it was?
Yeah.
You actually really don't. Like if the question is just like the electron configuration for germanium, but if you want to help you keep track, So it's germanium and it has 32 electrons.
Yeah.
Is that what you mean?
Yeah, that's what. Yeah, because they had that before on the one above.
Yes. Yeah, and that's just kind of telling you what it's going for, yeah.
Okay, you don't have to though.
But not really, yeah.
Okay.
Okay, now the question is, where am I starting after argon?
4s.
Good, so argon is here, which means 1 through, argon is 18. 1 through 18 is taken care of. So we just get to start here, which is the 4s. So then we'd have 4s2, 3d10, and then 4p2, and you're done. Does anyone see, how could we still check? Because before, if we added these up, it needed to add up to this number. So how could I still check it to make sure I didn't miss something?
You add all those to the 18 argons.
Yeah, just whatever this is, add that into your superscripts. Okay? All right, try the next one. Shortcut, what was it I gave you? Chlorine. Write the shortcut for chlorine on that line for me, and then we'll check it here to see how we're doing. Okay, ready to check it? Chlorine, you should have used, so chlorine is here. So you should have used neon to shortcut. And then it would just be 3s2, 3p5. And that's it. Questions on how we use the shortcut? Yeah, Will.
Okay, so let's say you were trying to get potassium.
Okay.
Would it be magnesium you would go from?
So potassium is here, right?
Or would it be argon?
Yeah, so the noble gases are just this column.
Okay.
So actually potassium would be really short, right? Because what would you use? You'd use argon, and then what would you have? Forest one, and you're done. Yeah, very good. Other questions on the shortcut? Okay, once again, you are free to use it every time now. You never have to go back to the long way if you don't want to. Yes, if you're bored and you want to, that's fine, but I don't recommend it. Okay, so then our next thing we're going to look at are some of these patterns that we see. So the first one is we know that the row number corresponds to the energy level. But be very careful, because that's the biggest thing we mix up, is that the D and the F don't line up with the S and the P's, right? The 3D, 4F, remember those aren't in line, okay? Another cool pattern that we have is the number of valence electrons are the elements in the S and the P of the highest energy level, okay? So when we've talked about valence electrons in the past, we can find the number of valence electrons by looking in the column on the periodic table, right? So we did everything in this column has 1, everything in this one has 2, and what did we do with the D block, or the transition metals? We skipped them, yeah, we ignored them, and then these were 3, 4, 5, 6, 7, 8. This is why we skipped them, is because if I write the electron configuration, let's say for bromine, okay? So bromine, I'm going to shortcut it, so we have Ar, and then we have 4s2, 3d10, 4p5. Notice that if I add up the S and the P, it adds up to my 7 valence electrons. So why are these not considered valence or outer electrons? What do you see, Holly? Yeah, they're actually on the 3rd energy level. And the definition of valence is that it's on the highest. So that's why we've always just skipped over that section, is because even though those are electrons being put in, they're actually being put into an inner level. So it doesn't change the valence at all. That make sense? Okay, and then like we mentioned, if you forget, the squares on the periodic table tell you the number of electrons in the sublevel. So if you forget how many can fit in the D, just count across and it goes to 10. Or in the F. Those are the ones people typically forget. Okay? All right, so then another thing that we kind of see cool as a pattern is that elements in the same column are going to have very similar valence electron configurations. For example, hydrogen, we know has the configuration of 1s1. If I go down the column, let's say to rubidium, so it's in the same family, its configuration is just 5s1. So we see these patterns in the families that it's very similar, and what will happen is next time I'll do a demo where we'll react a lot of this first family group, and you'll see that because this is similar, they actually have a very similar in how they react. Differences, because they're not the same thing, but they do have a similar pattern in which they react. Okay? Okay, so then there's 3 different ways in which an atom can be considered stable. The most stable an atom can be is with a full energy level. That's why our noble gases do not react with other things. Okay? No matter what you do, helium and neon will they don't react. You can pour them, mix them, heat them, cool them. They just don't react because they're already full. The bigger ones we find actually can be reacted a little bit, but for the most part, these are very unreactive things because of their full shell. What we also find, though, is we get a form of stability by also having just a full sublevel. Meaning, next time as part of my demo, what we'll do is I'll react sodium, so this is sodium right here, and this is magnesium, is we'll react both of those, and you'll see that magnesium is not as reactive as sodium because its s orbital, right, if I were to draw the 2 different ones, its s orbital is filled when sodium is not. So having a full box or full room also gives it some stability. It's not as stable as argon, because argon's all the way filled, but it does help it out a little bit. Okay? The other type of stability we have is also a half-full sublevel. What this means is that, like if you look at here in the D block, okay, with, let's see, that would be iron. So iron has 5 electrons in the D, and how do I put those electrons in? Get some of you all in their own, all pointing the same way. So this type of orbital also has a state of stability, being half filled. This is a little bit more stable than actually if I add 1 more. Or, same thing, if I go the other way and I take away 1, it's not as stable either. Having parallel spins on their own orbital is a form of stability in an atom. So what we see is this idea of stability helps explain why atoms do what they do. Is they're trying to find their way to get stable if they're not. Why they want to gain or get rid of certain electrons. Okay? So with this idea of stability, we see some exceptions. Okay? There's not lots of them, and there's mostly it deals with the D and then actually in the F block as well. But we're just going to look at the D block exceptions. So we wrote the electron configuration for copper. This is what you would typically write. Like if it was on your warm-up today, that's what I would expect you to write. But what scientists have found is that it's actually this. 4s1, 3d10. Any ideas of why? What do you think, Mitchell?
So the outer shell can have a full thing?
Yes, so now, so what has it done? Has it just added a new electron to get the 10?
We'll take it from the S.
So what it did is it took one of the electrons here and bumped it into this other room. And it's easy enough to do because these are very, very close in their overlap regions. So it's not like it had to move the electron very far. And in doing so, what happens if we draw our orbital picture here? Okay, so originally we'd have something like this. Wait, yes. What we've done is it said, okay, I'm going to take this electron here and bump it up over here, because now not only is this totally full, how is this classified as? Half full. And so actually now they have both of those forms of stability. Okay, so what we see here in the end is that copper gains stability with a full D sublevel. All right, ready? So here's what I want you to do. Here's another exception that occurs. So with chromium, this is what you would typically write, but this is what we actually get. So with your table, I want you to discuss and see if you can figure out why this is what it does. What is it achieving by shifting that electron around? Okay? 1, 2, 3, talk with your neighbor. What do we think? Go. To come to a similar conclusion. Okay? So one thing that Topher said was really simple, but I think is important here. Okay? That the reason why any of these exceptions occur is because what word did you say? Stability. Anytime you have to justify an exception, that's what you're looking for. Is like, okay, if it does this, this must be more stable somehow. So the next question is, okay, how is it more stable? So what did you guys figure out? So I heard a few people say because of half. What's the half? Jordan? Yeah, so we end up with 2 half filled rather than this awkward, not fully filled or half filled type thing. Yeah, Mitchell.
So is 2 half filled better than 1 full filled?
Mm-hmm. Especially because this D one is so big.
So is the outer one more important than the inside one?
Is the outer one?
Is to have the D full is more important than having the S full?
In terms of stability, you could say that we definitely see that trend, right? This is another reason why, if you remember when we talked about our transition metals, right? We talked about how we skipped them. Did I ever ask you to tell me how many valence electrons iron has? No, because this whole D block can often shift its electrons around. So sometimes iron has 2 valence electrons, other times it actually has 3. And that's why you never have to put it down, because it can vary in that D block. Same thing actually could happen in the F block as well. Because those orbitals are so close together, they're able to shift their own electrons around as they want. Yeah?
So does like chromium always exist in the 4s1 3d5? Like it doesn't exist in the 4s2 3d4?
Yeah, you could say that it's, well, no, because there are chromium. Oh, this is actually perfect. So chromium can exist as Cr+1 or Cr+2.
What does that mean?
Because the +2 is being that there's 2 valence. This one is that there's 1 valence. So it actually could be both. We see this is the more common form for sure, but the other one does exist as well. So, okay. Last thing with this stability feature kind of goes into the idea of our charges. Is what do we do about a configuration when an electron has a charge? So when something has a charge, that means it's either gained or lost electrons, meaning it's no longer neutral like you've been doing. But all you have to do is just take into account and add a few arrows or remove a few arrows. Okay? Remember, the overall goal is they're always trying to get to 8, right? They want to be like the noble gases. That's what they want to be, because they are stable, and that's the atoms want to get stable as well. Okay? So when we're looking at this, this is the common pattern we see with the charges, is that everything in the first column, okay, is it easier for this family to find 7 more arrows to get full, or actually if it just loses one, then it also becomes full because now that shell is just gone. So that's why this whole family is always a +1 charge. This whole family is always a +2 charge. These ones are always +3. We get this weird in-between group that could gain or lose, and then we see -3, -2, -1. The -1 charge means all this fluorine needs is 1 more electron to be like neon. Okay? So if I'm looking at oxygen here, this is its normal electron configuration when it's neutral. Based off what we just said with oxygen, what is the charge oxygen typically takes? How many more does oxygen need to make this P full? 2. So the charge that oxygen typically takes is a -2 charge. A -2 charge means that it's gaining 2 more electrons. So when we write the configuration for oxygen 2-, we now need to take into account that there are 10 electrons total instead of the original 8. So there's 2 ways you can kind of do it. The easiest way to me is if you just take the neutral configuration. So we're still going to have He, and then we go 2s2, because the 2 added electrons are always put in the highest orbital, or the one that's not full. And then we just get 2p6. Which element now is it mimicking?
Neon.
Neon. So what we say is this is an isoelectronic with neon, because neon's configuration would look exactly the same, right? Does this mean oxygen is turned into neon?
No.
No. Right? Electrons are just behavior. What would I have to do to change it into neon?
Not you can.
The proton number would have to change, and that's nuclear chemistry, which takes a lot more power. But think in your head, what would be another ion, and there's a lot of answers out there actually, that would be isoelectronic with neon? Can you write, you don't have to write the configuration, but can you think of an ion that is also isoelectronic with neon? Another element that would mimic and want to become like neon. I'll give you a second to think about that. All right, Austin, what'd you pick?
Fluorine.
Good, so Austin picked, do I have a periodic table here maybe to look at? So why did you pick fluorine?
So it needs 1 more electron.
So if you look, fluorine just needs 1 more, so technically we would say that it would be F with a -1 is isoelectronic to all 3. Good, have a smiley face. Anyone have a different one? Denise, what do you got?
Sodium.
Sodium, and what would it be?
Na1+.
Good, because if it loses, like sodium's 11, if it loses 1, it becomes 10.
So potassium would be
That's cool.
Yeah.
So can you have like oxygen that has that's isoelectric with neon without having a reaction happen, like without it combining with something?
Can this exist just on its own?
Yeah.
Mm-mm. Yeah. Oxygen -2 doesn't exist just by itself because it
So it
needs to
has to
get
react
those
with
from
something
something
to-
else.
yeah.
Yeah. Good. Denise, have a smiley face. Anyone else have another one? There's a few options. What do you got, Will?
Magnesium.
So you say magnesium, and what's magnesium going to have to do?
Get rid of 2 of them.
Good. So magnesium 2 plus all of these are isoelectronic. Have a smiley face. So that's good. Anyone want another one?
And
Ooh, I'm glad you bring this one up, Topher. What do you think? Would potassium ever
no,
be
they can't.
isoelectronic with neon?
I went during Sky Seven.
Why not, Jacob? Who would it be with? So they're always going to be isoelectronic with the nearest noble gas. Because to be like neon, potassium would have to lose 9 electrons. And they don't care what noble gas they're like, they just want to be like a noble